Alright, let's look at another problem. In this one, you're throwing peanuts off the balcony down into the pool below. So the first thing we're going to do is make an assumption that there's no air resistance. And for a peanut, that's probably a really bad assumption, but we really don't have the tools right now to deal with air resistance. So your model of the world has to be very, very simple. And as the weeks go by here in physics, you're going to learn more tools, and you're going to be able to deal with things like air resistance pretty soon. But right now, we can't. So let's make the assumption that we have no air resistance. And that means that this object is in free fall. Which means constant acceleration, and we can use kinematics to solve the problem. So if we're using kinematics, we always start off by defining the origin and the positive directions. So there are a lot of places here. It could be anywhere, right? The origin can be anywhere. But there are a few places that make the most sense. One would be at the bottom here where the swimming pool is. Another one might be where you're letting go of the peanut. Those are good places for the origin. Could be anywhere else, but those are the two I think that make the most sense. And then we've got a choice for our positive direction. We could pick up as positive or down as positive. A lot of people, when they become more familiar with these problems, they would choose the top here where you're letting go of the peanut as the origin and down as the positive direction, and then everything becomes positive and it's a little easier to work the problem. But most of us like to use up as positive, and we like the origin to be the lowest point. So that's what I'm going to choose. So I'm going to make this bottom point here my y equals 0, and I'm going to say up is my positive y direction. And now the next step, I always go about filling in this little chart with the information I know and the information I don't know, and kind of organize my thoughts. So there are 5 parameters that we need for these motion problems, and I make a little chart that lists the 5, and then I fill in what I know and what I don't know. So what we're really doing here is 2 problems, right? We have 2 peanuts. One peanut's thrown, and then a second later another one's thrown. So we're really working 2 problems here. So if this is for the first peanut, and then we're going to do it again for the second peanut. And so I'm going to put everything for the first peanut, I'm going to put a subscript of 1 next to it. So we've got a y initial for the first peanut, we've got a y final for the first peanut, an initial velocity for peanut 1, a final velocity for peanut 1, an acceleration for peanut 1, and a time for peanut 1. Those are my 5 parameters. And 5 because really all I care about is the change in y, right? But I like to explicitly write out y initial and y final. So those are the 5 things, and let's start filling in what I know. I know I'm starting out at a balcony, and that's 80 feet above my 0 in the positive direction. So that's a positive 80 feet. Remember, when you're doing these problems, y1 and y2, those are not distances, which would always be positive, right? Those are positions on a number line. Could be positive or negative, depending on which side of the origin you're on. We start out on the positive side of our origin, so it's a positive 80 feet. We end up at 0, and that first peanut is dropped from rest, so its initial velocity is 0. We don't know what its final velocity is. Its acceleration, we know, is 9.8 meters per second squared in the downward direction, and that would be the negative direction in our problem. And we don't know T1 either. I'm just going to call it T1 for now. So right off the bat, there are a couple of things that we can solve for. we can solve for the final velocity of that first peanut and how long it took. And then we can make a similar chart for peanut 2. So we've got y initial for peanut 2, y final for peanut 2. We've got an initial velocity for peanut 2, a final velocity for peanut 2, an acceleration, and a time, all for peanut 2. Peanut 2 also starts out at 80 feet. First thing I'm going to do, I don't like to mix units here, so I'm going to start converting over. My acceleration, I know, is meters per second squared. I guess I could have used 32 feet per second squared also, but I think it's just as easy to go and convert everything over to the metric system. So I'm going to change this to 24.4 meters. It's the second peanut starts and ends at the same place, but it has an initial velocity which we don't know, and it has a final velocity which we don't know. The acceleration is the same. It's downward, 9.8 meters per second squared, and the time we don't know. So if you look at peanut 1, we have 2 unknowns. And as long as we only have 2 unknowns, we can, in our 5 parameters, we can solve for those 2 using the other 3. But in peanut 2, it looks at first glance like we have 3 unknowns. But really, we know the time. Once we figure out what T1 is, we know that T2 is going to be T1 minus 1 second. And so we're pretty well set there. Once we know T1, then we'll know T2, and we can solve for the initial and final velocities of peanut 2. So let's go ahead and work on the first peanut. Start out by finding the final velocity of peanut 1. Final velocity of peanut 1. And so I'm going to pick one of my kinematics equations that's missing the initial, missing time, because those are my 2 unknowns. So I look for an equation that does not have time in it, and that would be this one. V final 1 squared is equal to V initial 1 squared plus 2a delta y. And so my initial velocity is 0. My acceleration is negative 9.8. So always keep those negative signs with you. My final position is 0. My initial position is 24.4 meters. And I'm left with a positive 478 meters squared per second squared. And now I can go ahead and take the square root, and V final of peanut 1 is, when you take the square root, always remember there are 2 roots, positive and negative root. So it's either going to be plus or minus the square root of 478. And that's 21.9 meters per second. And which root do we want, the positive or the negative root? The peanut's going down. We chose up as our positive direction. If we look back up here, the peanut's coming down. We chose up as our positive direction, so the velocity better be negative for peanut 1. And I'm going to just go back up here and put that in. So what we got here is a negative, what did we get? 21.9 meters per second. And then we can solve for the time. And so I'm going to use this equation, y final of 1 is y initial of 1 plus v initial of 1, t1 plus 1/2 a t squared. And again, I always like to start out by writing out the kinematics equation just as it appears in the book, because I like to start with something on my paper that's correct. Y final is 0. Y initial is positive 24.4 meters. I have 0 for my initial velocity. 1/2, my acceleration is negative 9.8. And my time is what we're solving for, right? And so I end up with t squared is 24.4 meters over 4.9 meters per second squared. And I take the square root. Now with time, the only root that makes sense is the positive root. We can't have negative time. It doesn't make sense. So I'm going to go 2.23 seconds for my time. That's t1. Sorry, I got a little sloppy there with my subscripts. t1 is 2.23 seconds, and I can go back up here and I can put that in 2.23 seconds. And that means that I know what t2 is. It's 1.23 seconds, and then I can solve for my initial and final velocity of peanut 2.